Hi, I'm Benedikt and I'll be presenting our work on multi-class segmentation from aerial views using recursive noise diffusion. Semantic segmentation in aerial images poses some unique challenges. We propose an end-to-end multi-class semantic segmentation diffusion model that addresses these challenges. We introduce recursive denoising to allow information to propagate through the denoising process, as well as a hierarchical multi-scale approach that complements this diffusion method. Finally, we show our method achieves promising results on the UAV ID dataset and state-of-the-art performance on the Weihingen building segmentation benchmark. Aerial images pose some interesting challenges, including diverse viewpoints, extreme scale variations, and high scene complexity. The examples shown highlight these challenges. Using diffusion models for segmentation tasks is non-trivial. Diffusion models are generally used for generation tasks instead of dense prediction tasks like segmentation. We find that trivial implementations of diffusion models fail to get good results because of the robustness of one-hot encodings. Simply adding noise to the one-hot encodings isn't sufficient, as we can see here. The resulting task is easy for the model to solve. To successfully train a diffusion model for multi-class segmentation, we propose recursive denoising. Training with recursive denoising effectively mimics inference, as the ground truth segmentation labels are not used as input. Instead, the process is initialized with pure noise. Training with recursive denoising involves progressing through each time step sequentially. This allows the error to propagate through the training process. Notably, the ground truth segmentation is never used as part of the input to the model. Instead, this process is initialized with pure noise. A noise function adds noise to the previous predicted segmentation. Then, the model denoises this noisy segmentation map conditioned on an RGB image. The model weights are updated for each time step. Compared to traditional training methods, recursive denoising prevents the model from hyper-focusing on the previous segmentation and forces it to learn to use the conditioning RGB image. It's important to note, recursive denoising is neutral to the choice of noise function, diffusion model, and loss function. The information propagated throughout the recursive denoising process is not limited to the error produced by the model from the previous estimation. We exploit the propagation of information by adding additional information. This is where our hierarchical multi-scale approach comes into play. By scaling the inputs to the model, this being both the segmentation map and the corresponding conditional RGB image, during the denoising process, we naturally increase the model's receptive field. We propose two scaling schedules. The first one evenly distributes the scale increases throughout the denoising process, while the second one increases the scale for each iteration. Once it reaches the largest scale, it resets to the smallest and loops. We use the first schedule for multi-class segmentation, while we use the second looping schedule for binary classification. We find this hierarchical multi-scale approach has a large positive effect on results, as we show later on. Before we go to the results, it's best to look at the noise functions that we use. For multi-class segmentation, we propose a softmax average noise function, which is both effective and controllable. For the simpler binary classification, we use a simple noise function, mostly to highlight, as previously mentioned, that recursive noise diffusion does not impose any restrictions on the noise function. Now for some results. Our proposed recursive denoising method achieves promising results, as shown here. Our method outperforms recently proposed approaches such as BANet and UAV Former. As expected, with a greater number of training time steps, the performance improves. This is shown on the table on the left. Interestingly, we show that decreasing the number of inference time steps after training the model on 128 time steps, the performance can still remain relatively high. This shows we could theoretically reduce the number of inference time steps if required, such as when computational power is limited or when accuracy is not of the utmost importance. This trade-off between computational efficiency and accuracy is a useful feature. Here we show the benefits of our hierarchical multiscale approach. We can see a clear positive effect, especially when we use 3 scales. This shows that our hypothesis of using the propagated information can be very beneficial. Finally, we show the results of our method compared to some others on the Wehingen buildings dataset. Here we see that we achieve state-of-the-art results, with both the best mean intersection over union score and F1 score. Lastly, we show some qualitative results from our method on the UAVID dataset and on the Wehingen buildings dataset. But we recommend you look at the paper for more details. Thank you very much. Please check out our code on GitHub.